Here's a genuinely hard problem for anyone building frontier AI. To be helpful, a model has to learn an enormous amount about the world, including sensitive fields like virology, cybersecurity, and nuclear physics. But the very same knowledge that helps a legitimate biosecurity lab could, in the wrong hands, help someone build a weapon. This is the dual-use problem, and it's fundamental. You can't cleanly separate the helpful facts from the dangerous ones, because they're often the same facts. So the question this research from AE Studio and Anthropic tackles is sharp. How do you keep the good uses of dangerous knowledge while denying the bad ones? Today, AI companies manage this with a stack of defenses, and each one has a real weakness. First, you train the model to refuse harmful requests, and you run classifiers that detect and block dangerous queries. But both of those are just behavioral layers sitting on top of knowledge the model still fully possesses. They can be jailbroken, and they have to be retuned for every new release. Second, you can restrict which users get which models, tiered access. But that works at the level of whole models and whole accounts. It's all or nothing. A user either gets every capability the model has, or they get a weaker model across the board. That's a very coarse trade-off. What you really want is access control at the level of individual capabilities. Picture a single deployment that includes advanced virology knowledge for a vetted biosecurity lab and excludes it everywhere else, with the model's general performance completely unchanged in both cases. Fine-grained per-capability control. The most direct way to get there would be to train separate models, each on a differently filtered dataset, and hand out the most capable versions only to the most trusted users. The problem is obvious. Training even one frontier model is enormously expensive, and training a whole family of them, one per capability combination, is simply not affordable. We need to approximate that family without paying for it many times over. That's exactly what this method delivers. It's called GRAM, short for Gradient Routed Auxiliary Modules. The core idea is to isolate dangerous knowledge into small, dedicated modules inside the model, modules you can switch on or off. Train the model once, and you get something that can imitate many different data-filtered models just by reconfiguring which modules are active. Flip a module off at inference time, and the corresponding capability is simply gone from the model. In their experiments, a single GRAM model approximates 5 separate filtered models, and it works from tiny 50 million parameter models all the way up to 5 billion. It builds on earlier ideas like demix layers and gradient routing, pushed to a larger, more realistic setting. So how is it built? Take a standard transformer. Inside every block there's an MLP layer, a bank of neurons. GRAM simply widens that layer, adding a few extra neurons that form a small auxiliary module, one module per sensitive dataset, say one for biology, one for cyber, one for nuclear. Now the trick is in how they're used during training. When a batch of biology text comes in, shown on the left, the biology module is switched on for both the forward and the backward pass, so it learns that material. When ordinary general-purpose core data comes in, on the right, the specialized modules are off, though a random one is occasionally enabled to keep everything working smoothly. And at inference, if you delete a module's neurons, you delete the capability with it. The subtle part is the difference between predicting and learning, and this is what the gradient routing in the name refers to. When the model reads biology text, it's allowed to use both its general-purpose weights and its biology-specific weights to make a good prediction. When it comes time to learn from that text, to update the weights, the biology module is updated far more than the general weights. And sometimes the general weights are frozen entirely. So the specialized knowledge gets pushed into the module and kept out of the shared backbone. And by tuning exactly how often you freeze those general weights, you get a dial that controls how cleanly the capability is isolated. Before the results, one quick idea you need, because raw loss numbers are hard to compare across different models and datasets. Throughout, they measure performance using something called the compute ratio, a compute-adjusted version of loss. Here's the intuition. For a given model on a given kind of data, it asks, how far into a full baseline training run would you have had to go to reach this same loss? A compute ratio of 1 means you match the full all-data baseline. A ratio of 1/2 means you're as good as the baseline was at its halfway point. Higher is better for capabilities you want to keep, and lower is better for capabilities you want gone. Their first experiment is a clean, controlled one. They use simple stories, a synthetic corpus of 2 million short children's stories, each labeled with one of 48 topics, like aliens or deadlines. They pick 4 topics to be switchable capabilities, pool the other 44 as core data, and train a small model with one auxiliary module per switchable topic. Look at the comparison. The top row is old-fashioned data filtering, 5 separate models, each trained from scratch with a topic left in or out. The bottom row is a single GRAM model, reconfigured 5 ways. When a topic's module is on, GRAM matches the model trained on everything. When it's off, GRAM matches a model that never saw that topic at all, one model imitating 5. Then they move from Toy Stories to the real thing. They train 800 million parameter models on web text code and scientific papers, plus 4 genuinely dual-use domains: virology, cybersecurity, nuclear physics, and specialized code, each just 0.25% of the data. And they compare GRAM against 3 alternatives: plain data filtering, LoRa fine-tuning on a filtered model, and a post-hoc unlearning method called Maxent. The result: ablating GRAM's modules removes a capability nearly as well as never training on it at all. On the domains it keeps, GRAM and LoRa actually beat filtering, and general performance stays right at the baseline. All 5 configurations come from that 1 GRAM run, where filtering would need 5 separate runs. But here's the question that really matters for safety. When you switch a capability off, is knowledge actually gone or just hidden? To find out, they hand the model to an adversary and let them fine-tune it on exactly the malicious data that was supposed to be removed. Data filtering, LoRa, and GRAM all hold up strongly. The dangerous capability does not easily come back, because it was never really there to recover. But Maxent, the unlearning method, tells a different story. Under that same pressure, it springs right back to nearly full strength. That reveals it never truly removed the knowledge, it only learned to suppress it. Deleting the weights genuinely beats merely masking them. A method that only works on small models isn't very useful, so they test how GRAM behaves as models grow. They train 7 models from 50 million up to 5 billion parameters, scaling the data chinchilla optimally along the way. Across all 4 measures, and at every single scale, GRAM tracks data filtering almost exactly, and so does LoRa, while each needs only about 1/5 of filtering's training compute. Even better, the safety properties strengthen with size. Bigger models fall further behind on a removed capability like virology and recover less of it under adversarial fine-tuning. So the approach doesn't just survive scaling, it gets more effective. That's a very encouraging trend. Now, in the main setting, GRAM and LoRa look pretty similar, so the researchers hunted for where they come apart and found 2 places. The first is composability, combining capabilities. What if you switch on several modules at once? With GRAM, they combine cleanly. Turn on all 4 modules and virology performance is just as strong as when virology was the only one retained. LoRa can't do this. Summing its adapters degrades performance across every category, and composability multiplies the payoff. 4 GRAM modules give you 16 possible on-off configurations from a single run, where data filtering would need 16 entirely separate training runs to match. The second advantage shows up when the data is messy, which is how real datasets actually are. Every experiment so far assumed every batch of text is perfectly labeled with its topic. So they broke that. They stripped the labels off half the data. For GRAM, they just train on the unlabeled data with all modules active, letting the right module quietly pick up whatever is relevant. The outcome is striking. With only half the data labeled, GRAM isolates the dangerous capability far better than either LoRa or even plain data filtering, the method usually treated as the gold standard. When labels are scarce, GRAM doesn't just keep up, it wins, and the researchers flag this as one of the most exciting threads to pull on next. The researchers are refreshingly upfront about what they don't yet know. There's the problem of entangled capabilities. General biology might be so intertwined with dangerous virology that no clean separation exists, which would undercut filtering-style approaches in the first place. There's the question of whether these trends hold at true frontier scale, and whether GRAM can be run in production without adding a lot of complexity. And there's the honest admission that GRAM and LoRa look so similar in most tests that they can't yet say, in general, what really distinguishes them, beyond those two specific wins. This is early-stage research, and it hasn't touched a production model. So here's the big picture. GRAM shows that a single pretraining run can quietly carry many different capability configurations at once, switchable simply by deleting a few weights at inference time. That's a meaningful shift. It moves safety access control away from the blunt instrument of giving out whole models per account, and toward a fine-grained dial where individual dangerous capabilities can be turned on for the people who genuinely need them and off for everyone else, without weakening the model's general intelligence. It's preliminary and not yet in production, but as frontier models keep absorbing more sensitive knowledge, the ability to modularize and control that knowledge, cheaply and at scale, could become a genuinely important safety tool. Thanks for watching.